So understanding big O. So how do you measure any two algorithms in terms of performance? You have two major metrics that you can actually use. That is, one is time and the other one is space or memory. So these two metrics are generally used to compare any of these algorithms. So if you want to compare algorithm 1, algo 1 and algo 2, considering that they run on the same hardware with the same clocking. So if algorithm 1 takes 15 seconds, algorithm takes 20 seconds and uses, let us assume, 2 megabytes of memory, okay, and this uses 1 megabyte of memory, okay. In terms of time, this is the best one, and in terms of space, this is the best one. So considering comparing these two algorithms, based on your use case, you can either choose algo 1 or algo 2. But in an overview perspective, where you don't want to measure time complexity with seconds or megabytes, we have to look at it from a point of the number of calculations that are happening in any particular algorithm, right? So what we do is, we first we will just check out how time complexity is calculated in any specific algorithm. So yeah, if I write a for loop, for example, so in this particular case, the time complexity of this entire loop is around O of n. And why is that? Because there are n number of calculations that are happening. This particular statement is getting run n times, right? So it takes total the worst case scenario for this particular function to end is O of n. So O of n is the time complexity of this particular loop. Now if you want to calculate furthermore as to what are other types of time complexity that we can have. If I nest a loop within a loop, let us assume that I have nested a for loop within a for loop. I'll just leave a space in here, or else it will take it as an arithmetic calculation, right? So yeah, so in this scenario, the time complexity of this entire function, let us calculate layer by layer. For example, this internal for loop will take n calculations like we discussed, and the external function will take n calculations to complete. So the worst case scenario for either of the entire function to complete is n cross n or n square. So O of n square is your entire time complexity, and time complexity is always the worst case scenario. It is not the best case, but it is rather the worst case of any algorithm that you're trying to analyze. Okay, so now we'll be looking into the best time complexity that an algorithm can have. So the best time complexity that any algorithm can have is where the number of calculations do not depend on the value of n. So regardless of how high the value of n is, the number of calculations should remain constant. So if you have a function, okay, where you're taking the number n and you're just returning, for example, let us assume that you're returning this particular value, right? So the number of calculations that this entire function takes is only 1. So regardless of how high the value of n is, your time complexity will be O of 1. So this is the best time complexity that any algorithm can have. Okay, so now we'll be looking at different time complexity. Assume that you have an array which ranges from 1 to 8, and you have developed a searching algorithm based on the divide and conquer method, and you want to search where 1 is located in the entire span of the array. So what you do, for example, you go with the elimination method. First you check, is the number 1 greater or lesser than the middle of the particular array. So if you divide 7 by 2, you get 3. So in integer format, so you compare, is 1 lesser than or greater than your value at 3. So the value at 3 is 4. So what do? You can check, you can say firmly that yes, this particular value does not exist in the right half of the array or greater than the middle number. So you can eliminate this entirely, right? So now we have done one operation. Now I'll recheck with the other half now. So other half I'll check, is 1 greater than or lesser than 1. So you can see that it doesn't belong to the right half of the array again. And you do one more operation to find that 1 is belonging at the 0th index, right? So the worst case scenario, it took you around how many steps? It took you around 3 steps, and there are around 8 indexes over here, and it happens that 2 to the power of 3 is equal to 8, right? Okay, so now you can say that since it took you 8 operations, right, and 2 to the power of 3 is equal to 8, and log base 2, right, log base 2 to the power of 8 is equals to 3, right, when the indexes were 8. So the number of the time complexity of this particular algorithm is log n. Log n is the time complexity of this particular algorithm whenever you use the divide and conquer method in a searching algorithm of sort or whatever use case your particular algorithm is seeking to, right? So the time complexity is log of n. So this is one of the best case scenarios of time complexity after O of n, O of 1. Now, since we have discussed around 4 major time complexities, one is O of n, right? Next is your O of n squared. Next your O of 1 and O of log n. You also have O of n log n, which is also present. This is also a particular time complexity. And majoritarily, for the way you avoid constants in calculating your time complexity is that if you have 2 functions side by side, okay, and there is a for loop over here, there's another for loop which executes n times, which also executes n times, okay. This also executes n times, this also executes n times. So your time complexity will be what? O of 2n, right? But by the law of avoiding constants, we can ignore this, and the entire time complexity becomes O of n. We usually don't consider constants while calculating time complexity of any algorithm.